stuff maybe to the second whole, where they can tell the shapes. Yes.
Now I'm going to go straight to timber versus steel slides. Now there's a whole bunch of resources in here. I'm not going to go through it all because there's so much when it comes to framing. You've got all this at your fingertips. You can pour through all this at your own at your leisure. You can even download these things and save them elsewhere for future reference. There's really so much to learn about framing. If I could talk to you for several years about framing, I would, but we'll have to move on. So all this stuff is there for you. I'll go to the slides that have a lot of the, covering most of the things. So we've got a few different options for framing. In terms of materials, we go with either timber or we go with steel. However, there's a lot of places built that will incorporate both as well. So we start bringing some steel into our timber frames. The most common approach to that is, see if I can find one. No, there's not a really good picture of it. But we'll have a timber frame, and then we'll have some large open areas that we can't actually create using timber alone, because steel is far better for both its compression and tension per cross-sectional area than timber can be. You'll use steel in sections, but your steel is going to be really expensive. So for some of these portal frames you introduce, you might drop $10,000 on just that. So it's a very expensive thing to go thinking about incorporating a lot of portal frames. Use them wisely, use them sparingly. Although I'll revisit that statement later when we start talking about more the industrial style construction. So that's our timber frame. This one's a two-story. We've got, it appears, that's conventionally pitched roof. I can't see any nail plates in there, so conventionally pitched roof. We've got loads happening in that roof onto walls that are transferred to floors. So we've got a suspended timber floor here, so we've got floor joists running through, and then we've got loads then imposed through other internal walls down to the concrete slab. This one, we have much the same stuff happening. If you look at both of these frames, essentially what's happening is a lot of the same stuff. We've got steel with essentially rafters at similar sort of spacing. So if that's a tile roof, they're going to be at 600. If it's a sheet roof, they're going to be at 1200. But and we've got a lot of the same terminology. But what ends up happening with steel framing is because the truss actually is a very efficient, materials efficient approach through sharing a lot of its loads with everything. What you see with the modern light gauge steel frame houses is there's actually the concept of the truss is incorporated through so many aspects of the building. So with timber, we're typically using trusses for roof sections. We build a truss roof. Certainly you build a trussed roof with your steel as well. So you have manufactured steel trusses that are manufactured in the factory, but also your wall frame sections will be manufactured in the factory as well. And they're typically now calculated as essentially being trusses as well. So we can see this little opening here. So we've got a large window happening there. We've got this bit happening above. That is much like a lintel in your timber framing, and these are much like your jack studs, except that because of the way that these are fixed, that whole thing is working as one. So that's working like what is actually called a ladder truss. But you'll also see steel frames about where you've got those jack studs on an angle that end up working like webs in a truss. And I'm not expecting you to understand the complexity of all the design and engineering at this point in time, but when you're driving around, you've got some spare time and you're going through new housing developments, and you look at things, have a look at these light gauge steel framing and see if you can identify where there are actually trusses incorporated in the whole thing, and you'll start to see trusses everywhere. Another major difference between timber frame and this steel framing is we were talking about trusses. Once we go with trusses, that's in the engineers or the truss manufacturers' hands. They do the design, and any modification that has to happen goes back to them. When we've got our timber frame design, if we've got a thorough understanding of AS 1684, we can design that in accordance. So we can use all the rules set out in that to design this. When it comes to designing this, we can't. We don't actually have an Australian, well, there's the NASH standard for residential steel framing, and then there are Australian standards that relate to the use of steel in buildings. But what we can't do is design this ourselves. The reason for that is because each light gauge steel manufacturer has their own profile that they make out of their own steel. Each of the sectional properties of those steel members are different, and they have their own design software. That design software is incredibly important to them and incredibly expensive to develop. So they hang on to that. So if you want a steel frame, yes, you can design it, you can have an understanding of how steel frames work, and you can have an understanding of those manufacturers' parameters, but you can't just go, all right, yeah, I'm just going to sit down tonight and design a steel frame. That's not going to happen. You have to take your design to the manufacturer. Manufacturer puts all that info in and goes, yeah, it's going to cost you 12 grand. And we can supply in 6 weeks. That's your only option when it comes to the light gauge steel framing. But we should still understand it, because if we understand what's going on, if we understand what the parameters are, we can work best with those manufacturers for getting the results for our client. Also, another thing that relates to that difference between the two, so timber we can design with AS1684, steel has to go to the manufacturer. A lot of your smaller scale designers, like when I say small scale, you can still have relatively large building companies, designers that work solely in timber, but a lot of your steel framing is done by larger housing companies, the bigger ones, because if we can't, because we don't have much control over that, we can't really do much bespoke design with it. So if we're going to be designing stuff from scratch, working with clients and going, okay, we can do this, this, and this, and work through it, it's going to be far simpler for us to do that with timber, rather than if we go, yeah, we can do all that, I'll have to send that off to the manufacturer and find out if we can do that. Yeah, we can't provide that same level of service. So you often get timber being used by your smaller people, or people who are doing designs from scratch, and then steel by people who are punching out the cupboard or the Mooter or whatever, that house design that stays the same for everywhere it's placed. It might just be turned around, because that's going to be much simpler. Yes.
Why we choose steel framing? Why we choose timber framing?
Right. The reason we choose steel framing over timber, the reason why these larger companies will go with steel, is because, like our truss roof, that can go up really quickly. And with steel framing, it can go up really quickly as well. It's just all these little pieces, they're all chopped and manufactured by a robot in the factories. Well, there's a roll former, this roll forming machine, and we'll see some videos about that later on. That's just chopping off all this stuff and punching it all out, punching holes and everything, and then it's all assembled in a factory. They put it all together. All these pieces go out to site. That frame goes up incredibly quickly. So there's a lot of efficiency in there. So that's why we would use steel framing, because it's all done in the factory, and when it's all done really efficiently like that, it can be done much cheaper. That's why we would use steel. The reason we'd use timber is because we can have more control over that. that's the main, mostly when we talk about buildings and building decision, it comes back to economics. Sometimes it comes back to client preference or other considerations. So with timber, timber is a renewable resource. It's like grass, essentially. You know, it can be grown and cut down, grown and cut down, grown and cut down. It takes a lot longer. It might take 10 years or so, or longer for these trees to reach the point at which they're financially viable to be cut down. But it's a renewable resource. We can keep growing timber. It takes carbon out of the atmosphere. It locks carbon away in that frame. Whereas steel is not renewable. There is a finite amount of iron ore in the ground. That iron ore has to be dug up, has to be cooked with coal and molten, turned into this steel. There's a lot of energy input into that, and then that steel gets used. So, and it doesn't store any carbon. So it has a high embodied energy, but it's not actually, giving a net benefit in a carbon reduction sense. So there are a lot of other factors that come into it. Another big difference between timber and steel is the way it will behave in a house fire. Timber will maintain a structure in heat. You can get timber really hot and it maintains its structure, and as it burns through, it gets weaker and weaker and weaker and weaker and weaker like this as the charring gets closer to, because your cross-sectional area with timber, the structural cross-sectional area is the uncharred amount. So as it gets burned more, it gets weaker. But steel, you get that to a certain temperature, it just buckles and gives in. So there's differences in the way that it will behave at fire. Also, your steel expands and contracts a lot with temperature outside. So some of your steel frames, when you've got the steel roof on them, can creak a bit as well, because the whole thing is going like this. Those joints are creaking. Steel has much more conductivity than timber. So if we put a piece of timber on a hot plate in the kitchen, and we put a piece of steel on a hot plate in the kitchen, I'd much rather touch the piece of timber. It's not transferring that heat to the same extent. Same thing's happening in our buildings as well. We get heat from the sun on our steel sheet roof. That goes to steel purlins, which are attached to steel rafters, which if we've got a flat ceiling, they're attached to our ceiling. That heat is transmitted directly through all of those members. If that's a piece of timber, and the steel sheeting gets hot, our batten gets a little bit hot, our rafter doesn't really get very hot, and then our ceiling, we're not transferring it. So they're the main differences between them. But most of the decisions simply rely on economics. So the customer goes to this house designer or that builder and says, "What can you do it for me? Like, how much is it going to cost me?" They go, "Oh, it's going to cost $230." And you go to the steel one, and they go, "Oh, we can do that at $225." So that's the main difference.
Does that have anything to do with taking up earthquake vibrations or cyclonic zone areas? There we have to use steel framing stuff.
Certainly in South Australia, we don't consider those things. So we're not in a cyclonic area. So that's not a thing which is factored in. We're also in a very stable part of the world. Yes, we do have seismic activity happening here in Adelaide, but it is very small. It has been very small to date. There's nobody saying we have to design for earthquake loads. Look, your failure in timber structures typically happens at all your joints. It's about your fixings and how your joints are constructed. And so for that matter, I'd say essentially a steel frame will perform better in both of those scenarios because they have much stronger joints. Those joints are engineered and they're controlled, and there's a lot of homogeneity. All those joints are going to be the same. They're going to be quite reliable. Whereas in a timber frame that's built on site, you might have your carpenters just start firing nails in. They're doing it very quickly. They do it every day. They might actually hit a dead knob or something, and that nail goes like this. Doesn't actually, provide, and they might not know. That will be your weakest link. And any structure is only as strong as its weakest link. So there's a lot more variability when it comes to timber frames. So just off the top of my head, that's how I look at it. But yeah, I think if you want to go down that, it's a relatively complex.
Just to continue on with the earthquake thing, I think the largest earthquake we've had in Adelaide was like 5.6 on the Richter scale.
Yeah.
Compared, and that was like 1956.
Yeah.
Damage.
It did, but 5.6 compared to places in more earthquake-ridden areas that get them not only more frequently but more powerfully, 5.6 is nothing to those places.
Depends on where the structures are.
And on that, it was interesting. So when I was working at the engineering firm, through the time I was working, we had 2 small earthquakes in Adelaide, and we would get a flurry of work come through at that point. Yes, some of it is because people are being opportunistic, but what we would do is we do work for insurance companies. So people lodge a claim for insurance, and then the insurance refer that on to us and say, can you do the analysis of this situation? Can you provide answers and solutions to this? So you get a flurry of work coming through. Yes, some of those people are being opportunistic. Other people genuinely had cracks and things opening up at their houses with those events. But what you can actually have happen, and I sort of covered this earlier on when I talked about dilapidation reports, is you can have scenarios where you've got some pressures acting on a building and they're slight and they're gradual, nothing's happening. You provide a small catalyst for things to shift, a little bit of agitation, and they can go. So sometimes you can have very small earthquake events that are the straw that breaks the camel's back, essentially. But still, on the scheme of things, we're talking incredibly low numbers. So we might have, for all of Adelaide, for that event, we might have a dozen extra jobs. So, it's not a major consideration. Because the worst one we've had, as you said, 5.6 on the Richter scale. So back to our timber versus steel. So touch framing, steel and timber. Most common is timber. These slides may have to be updated in a couple of years because we're getting a lot more steel coming through. As that design software becomes together.
Can all of the trusses be prefabricated?
Basically. So a lot of your trusses are pretty much always entirely prefabricated. Can the timber? Yes, certainly. Yeah, and there is a bit of a move toward that as well. Because your wall frames are actually really quick and easy to do on site in the main, there's not a great deal of motivation for doing that. If we're going to be working on a concrete slab, which is all nice and flat, it's actually a very simple thing to be knocking up wall frames on site because all of your studs are going to be the same height. So that's your vertical members in your wall frame. They're all going to be the same height. So you send your apprentice over, go, look, I need 18, 20 or whatever of these studs or this height. They're just chopping them away like this. And then you go laying it out on your floor slab, shoot some nails in, tilt it up. So there's not a great deal of efficiency gained by doing that same work in the factory because wall frames are very easy to do. They're vertical members and they're horizontal members. So wall frames are very simple. So for that, yes, there are people who are doing prefabrication of wall frames or structural elements within a factory, but in the main, there's not a great deal of efficiency that happens, but there are limitations. So if we're prefabricating stuff in a factory, one of the limitations is we can't and we shouldn't go making modification decisions on site. Sometimes we can. and also it has to be transported. So the size of these elements, and then also they have to be lifted. If we're building a wall frame on the slab, and then we just tilt that up with 1 or 2 people, that's fairly simple, and then you put your temporary bracing in, and it's done. If you have to lift that wall frame off a truck, you have to be very careful with lifting that wall frame off a truck and not twisting it and things like that, and then that has to be handled into site. So not a huge amount of efficiencies from manufacturing in the factory, but what you do see is approaches, other structural approaches, things being, and we'll cover cross-laminated timber later on, but other uses of timber where we get plywood, cross-laminated timber, all these sorts of things that can actually just be made by robots in a factory. So we get CNC routers that are controlled by a computer program. You can say, build us that, like we do the drawing, it's this thing, okay, robots and machine, build that for me, and then that all happens like that. There's certainly efficiencies that can happen in that regard. We'll get to all that later. When it's your simple, fairly cheap residential timber, largely happens on site unless it's your timber roof trusses. So we've got to think about loads, we've got to think about vertical loads. So we've got gravity acting on everything. Gravity is going to be there every day. We wake up and it's going to be basically the same. Horizontal loads, that are wind loads, they will differ. Your wind loading at the beach, near the airport, etc., these large open places, that wind loading is going to be more than if we're building in a protected suburban environment. If we're building right on top of a hill, we're going to cop a lot more wind than if we're building down in a valley. And then, of course, wind differs from day to day. But those different locations in which we can build, we have wind speeds that are determined for our state, and everybody's seen this, we've gone through this in their SAMAP viewer, where we can get the wind speed of locations for certainly around the metropolitan area. When we step out of that, we have to do independent assessment or individual assessment. So as per AS 4005, work through that Australian standard to work out what the wind speed is for that location to get our loads, because our loads are going to determine how much bracing we have in that building, primarily. So the wall frames have to be strong enough to resist those lateral loads, so loads from the wind pushing sideways, and also the gravitational loads, everything that's imposed on top of the building. To do that, and you've got to learn this in your timber framing design, or you'll learn to do that next semester eventually, but with your timber frame design, I'm hoping you'll go through different stress ratings of timber. So there's some species of timber or timber grown from a particular tree which is going to be stronger than another one. If we have timber grow really slowly, let's say we've got a piece of radiata pine. Pinus radiata, that's the most common pine that we go building with in South Australia. We've got stacks of that growing down in Mount Gambier. We've got a bit growing in one place. Let's say we've got a piece growing in Mount Gambier and we have a piece growing in the Adelaide Hills here. It's going to end up like a tree, and we chop those down, we're going to have a different stress gradient for both of those, the timber that comes out of either one of these. The one that grows slower is going to have smaller grain, and typically is going to be higher stress gradient. So that, by and large, when you're designing anything, you design it as per the MGP 10 standard tables. MGP 10, that stands for machine graded pine, and the grading is 10. If you look around at a lot of house frames, you'll see these little stamps on there, and it will tell you the timber species, the hazard class, and the stress grading. And by and large, you're going to see MGP 10 written around everywhere. Sometimes you see MGP 12. As a designer, I think it's always much better to design everything with MGP 10 than 12. 12 is slightly stronger than MGP 10, but not every piece of timber is going to be MGP 12. If you, as a designer, go, all right, this one we're doing MGP 10, that one we're doing MGP 12, etc., then your builder has has to take that timber take off to the timber supplier and say, we need some NGP 10 of this and NGP 12 of that, and the timber supplier might say, don't have that in NGP 12. Got it in 10, not 12. All of a sudden, that NGP 10 piece is not strong enough to handle the design. Or if it gets incorporated, then the design is deviated from what was supplied to the council, hence, the builder is in contravention of, the Planning Act. So, if you design everything as MGP 10, then the timber supplier will go, oh, we don't have that in 10, we've got it in 12. You go, oh, 12 is fine. Because that's going to be stronger. For that same size piece of timber, you can add that in. You're not making a deleterious structural decision, so you're fine. But you're not going to design everything with MGP 10. Some of your timber methods, like all of the stuff that's external, the stuff that gets exposed to weather, things like this bit here. This bit here is the fascia. That's going to get weather on it. It's going to have a gutter joined onto it. In between the gutter and the fascia, you're going to get moisture collecting in there. You get little bits of dust and dirt and all sorts of stuff that harbors moisture in there. You want to really protect that timber. You look around at houses, the bits you see starting to weather and starting to look bad once they get sort of 20 years old or so are your fascias and your barge boards. Those are the bits that cop a lot of weather and start looking poor very quickly. You're going to want to use something that's called LOSP, which is light organic solvent protected pine. Now that LOSP, you also want to typically have a stronger stress rating for it. It's not so much about its low bearing capacity, but about its actual the timber's integrity. So a very common specification for timber, and I'll actually write this down if you can, or try to remember this, is for all of your exposed stuff, you use H3 like F7 H3 LOSP. Yeah, now that's a good one so with pretty much all the drawings I do specifying timber, the engineering firm, engineer would be writing F7 H3 LOSP for all the external exposed elements. And that's going to be, if you're buying a post for your veranda, a piece of fascia or so, it's going to be primarily F7 H3 LOSP. That F7, that's a stress grading. So like NGP is a stress grading, so is the F grading. Now the F grading, that can be used for any piece of timber. So I can get a piece of jarrah, and that would be F27 typically, or F17 if it's a new piece. If I get a piece of pine, it's going to be F7, F17. But that stress grading of NGP, that's specific only for pine. So NGP is machine graded pine. So I can't buy a piece of jarrah that has an MGP rating because jarrah is not pine. So MGP is solely for pine. Does that make sense to everybody? You've got these two concurrent stress gradings. The F grading is used for any piece of timber at all, whatever species of timber it is. Your MGP is solely for pine.
Is the process the same? I mean, for F and MGP, process of grading is the...
Oh, no, the process of grading is different, and that's actually a really good question. So you can have an engineer or a timber grader visually grade timber. So they can do some push tests and stress that and test that stress, or they can look through the knots and grain size and all this sort of stuff, and they say this piece of timber is this particular grade. Whereas NGP, that's machine graded pine. So that a machine does the grading for that. So it goes through this machine, the machine's pushing these things against it, going, oh, it's this strong. That's what it is. It's NGP or NGP 10 or 12.
I mean, all other pieces of timber can't be machine graded, no.
Yeah, I don't know the intricacies of that and why that is the case, why we don't have machine grading the various different timbers. but it might also be just a thing of commonality. So the bulk, like so much of our timber is pine. We have a lot of pine which is grown in places like Mount Gambier, and that's what we use primarily for building is, so much of it is pine.
For flooring, that is just visually graded for the flooring.
Yes, so you've got visual gradings for flooring as well. So you've got both hardness and stress that you have to consider. You also have to consider what things look like as well. So you've got your, when it comes to house structures, by and large we're using pine, and so your pine is like, let's say that's 99% of the market, and then you've got this small 1% or 5% which is taken up by a dozen other species. If I was going to make a machine for grading a particular type of timber, I'd make one for grading pine rather than these other species of timber that are competing for that very small percentage of the market. Places we do use hardwoods are if we want to make something termite resistant. So termites eat pine. They'll actually eat mostly. They don't eat. There's an native pine in the Flinders Ranges that termites don't eat, but also things like your jarrah, your ironbark, turpentine, those Australian hardwoods. Termite, if they're dry and they're kept dry, termites don't want to touch them. They're just way too hard to eat. They don't bother. So you've got stumps up off the ground. You might want to use an Australian hardwood for that, and you wouldn't want to use pine. The only way you use pine in that sort of scenario is if it's treated, so CCA treated pine. I'll follow back. So we've got our various different SF ratings of timber. That's primarily about its load-bearing capacity. So truss roof, non-load-bearing internal walls. Gone through a lot of that. So we have to keep working through this relatively quickly. With our wall framing, so earlier I was saying that there's not a great deal of efficiency gained by producing your wall frames in the factory, and you can sort of see that by looking at these wall frames and think, well, that's actually really quite simple. We've got lots of vertical elements, so all of our vertical elements, they're called studs. Then, right at the top, holding all those studs together is a top plate. At the bottom, we've got a bottom plate. So primarily, a wall is studs with top plate and bottom plate. Those studs, when we impose a load, like let's say we're putting a huge weight on that stud is going to want to bow sideways. It's going to bow one way or the other. So to help with those studs from bowing, you put noggins in here. So those noggins, they provide that lateral restraint to stop the studs bowing in one direction or another, and they also help the share of load between studs. If we have a huge weight on top of this one wants to bow, but it's restrained by the stud on either side of it by that noggin, etc. And those loads are transferred to the wall frame in this direction. So we've got studs, top plate, bottom plate, and noggins. Now, if we're not doing any openings in those walls or any intersecting walls, that's all we've got. So the wall frame is incredibly simple. It gets a little bit more complex when we go putting a window in. So when we put a window in, we have, rather than loads being transferred through every stud, like a roof framing landing on top of those studs, transferring those loads through, we have roof framing landing on top of this, putting a load. That load has to be transferred to the studs on either side. So that load is transferred by this thing called a lintel, which spans that opening. Because what we don't want to have happening is loads happening directly on top of the window. If you've got loads happening on top of a window, it doesn't take much weight to make a window crack. So you want to have a little bit of clear distance between your lintel and your window frame as well to allow some deflection without imposing any loads on your window frame. But we have that lintel happening over there. Now, because that lintel is taking the weight of all that roofing above it and distributing that weight to the studs on either side, in the vast majority of cases, we will have to have extra studs in there. So working through the timber framing code, Rosemary should show you why and where we increase the cross-sectional area of our studs. So that's the terminology for saying put an extra stud in there. So our studs be, let's say they're 90-35s, stick two of them together, all of a sudden we have a 90-70. It's increased the cross-sectional area. Now, as I said before, your pieces of timber like your 90-35s is less than $2 a linear metre. We can sit down and spend 15-20 minutes designing, working out what these loads are going to be, and deciding, do we need one stud or do we need two studs? At $5 a stud, probably better, your time-wise, go studs, all openings have double studs. And then for where you have even larger point loads, you go to triple studs. So some of those situations you can work through the timber frame code and make all these decisions, but sometimes when it comes to studs, what we used to do in the office is just have a note on our timber frame that says double studs to all openings. And then, that's problem solved. Double studs to all openings also enables really nice seating of that lintel. So if we've just got a single stud happening there, we have to chase out our stud a little bit to help accommodate that lintel. That single stud which is there is then compromised because it's got a piece chopped into it. Now we can chop 20 millimetres into a stud without that being considered as compromised to the timber framing code. But 20 millimetres is typically not going to seat a lintel inside there. The thinnest lintel you're going to get at 35 millimetres, it's going to be sticking out 15 millimetres. So pretty much any scenario of fixing a lintel in there is going to compromise the strength of your stud, even if we're seating the lintel between our studs and putting bugle back screws through to help pick up that lintel. So providing double studs means that we can chop one of those studs off short. So our jam stud, we chop that off short, our lintel sits on top of that, and then we fix our lintel into all of those pieces of timber. It makes a really nice seating arrangement for that lintel, and it's really easy to fix in a very strong manner. So by and large, that's what you do, you say double studs to all openings. Also, the other things we can see is when we get an intersecting wall, we have to put some blocking in here, and then we have a stud arrangement that enables the fixing of our plasterboard. So our plasterboard needs to be fixed at all the corners. We can't have studs back from the corners and then have sections of plasterboard cantilevering past our studs with the potential of flapping around, because there's no strength in that. And we will put in our corner piece for doing the flushing of the plasterboard, but if there's no strength in that, then that will crack very quickly. So we want studs in corners. We have to think about how we can provide fixing to plasterboard on the faces of our studs. So typically the carpenters will do their arrangement of the studs at that point in time, but there are times that you as drafters have to think about the arrangement of studs. If this is going to be a brick veneer house, then we don't actually have any fixing happening on our outside face of our studs there. So we don't have to think about creating faces for fixing. But if we're going to be putting fibre cement sheet or timber or some sort of cladding on the outside of this frame, then we have to think, how are we fixing that cladding right on that corner? So we have to provide a face for fixing and a face for fixing. So you think about your stud arrangements there. The common terminology for that is your stud cluster. So it's how the studs are clustered together in a bird's eye view sense to ensure that all your sheet material that's fixed on there is fixed on there correctly. Moving on, so we've got our lintels, we've got our jam studs, and then these little ones here that are chopped off, they're called jack studs. Got our lintel trimmer happening underneath, also known as a head trimmer, and then your sill trimmer happening, your lintel trimmer having at the top underneath jack studs, and then your sill trimmer happening down the bottom. These ones are also jack studs down the bottom. Beyond that, then we have our bracing, and we've got two types of bracing shown in this. So one of them is your galvanised iron strap bracing. You can buy 30 metres of that for about $10. So really cheap stuff to buy, a little bit time consuming to install, because you put it over the top, shoot some nails in, and then, well, you put it down the bottom, and then take it over the top, shoot some nails in. While you're stretching it, you put your claw hammer in, you stretch it over to get a bit of tension in it, and then you tension it up with your little tensioners that go in there. So it takes a little bit of time to put in there. That will give you between 1.5 kilonewtons and 3 kilonewtons of restraint per linear metre of that bracing. Over here we've got some sheet bracing. That bracing, if you're not cutting it or so, it goes in fairly quickly because that's nailed in place. You put it up against your studs and you shoot nails in it at 200 centres or 150 centres, whatever the manufacturer specifies. So you shoot your nails in, goes in fairly quickly. That can produce between 3 kilonewtons of restraint and 6 kilonewtons of restraint per linear metre. So you get far more bracing capacity from your sheet bracing. But that's going to cost $20 a sheet. So, however, one approach I'm a bit of an advocate for is because, and you see it a lot now with the buildings that are built, starting to be built over the other side of the car park as you come in from South Road, you drive around there, you'll see actually they're all pretty much clad now and you can't really see the bottom sections of them, but when they were being built, they had sheet bracing all the way around. So the whole bottom section is covered in sheet bracing. To do that sheet bracing all the way around, it's going to cost a few $100, which is not actually a very big expense in the whole scheme of things. But if you provide that sheet bracing all the way around, you get an incredibly rigid frame, so it ties everything together really well. But you also get compartmentalisation of that frame in terms of airflow. So when it comes to insulating your house, yes, you put insulation in between your studs, but then if you've got sheet bracing, a sheet covering all the way around, that helps lock that in. It creates these air pockets and it provides you with additional insulation. So for a few $100, you can get a really rigid frame and this wall frame which is all fully sealed. And particularly if you're going to, if it's a brick veneer and you're not fixing to the outside of it, it's not a consideration. But if we're going to use some sort of sheet material for lining out that wall frame, what we can't do is use sheet bracing in one spot and then strap bracing in another, because that sheet bracing is 6mm thick. The strap bracing is 0.8mm thick. If you've got sheet bracing and then strap bracing or no bracing, you've got this 6mm bump. And if you put your sheeting straight on top of that for something, that bump has to be accommodated and you'll end up, when you look down the wall, you'll see a little bit of this going on. So if you're using sheet bracing, one of the drawbacks of it is for your unbraced section, you have to pack those studs out. So with the circular saw, you just cut off lots of strips and you nail that to each of your studs. Or you just brace the whole thing. Carry that sheet bracing all the way through. So I like that approach personally.
What material is that sheet bracing?
So that sheet bracing traditionally is hardboard. Now if I flick right back up to the first one there, that dark coloured stuff, that's hardboard. And in your timber framing code, you have a section there. When you go into bracing, it's got a section for hardboard. It's got a section for hardboard and for plywood and also for the strap bracing. What it doesn't have a section for is OSB. But OSB is what pretty much everybody is using now. So OSB is oriented strand board, which I'll quickly Google search because I'm sure like once you see it, you go, oh yes, I know that stuff.
What people what?
Can you use blue board? Maybe. Don't know.
I think so.
Yeah.
I think I saw that.
Yeah. That's something I've never explored to using. Okay. Okay, to help provide structure to tie that.
And the wood is more resistant.
Yes.
Why? Because garage door they are exposed much.
Okay. Yeah. Okay. Yeah. Cool.
When they
Yeah.
build my house.
Yeah. Yeah. Maybe that's something. Yeah, we'll have to explore later on. But I'll take your word for it. Yeah. Does everybody know that stuff? Has everybody seen that stuff before? Yeah. So that's Orrington strand board. So there's a company called. Actually, I can't remember. There's the Gunnarsons are the supplier, but then there's some other manufacturer that manufactures. Anyhow, that manufacturer, they say, use this OSB, it provides you this much kilonewtons of restraint for this meterage if it's fixed in this particular pattern for this particular size. So rather than referring to the timber framing code, you can just refer to their product literature and use this for your sheet bracing. This is, because it's really cheap, that's becoming the mainstay of what everybody uses in terms of sheet bracing. But over garage doors, that might be different. I'll have to have a look at that for water resistance and also for additional strength.
Because they put the bricks, you put the cable.
So in that section you didn't have any other.
The cable, that they put the cables, I think I saw the globals there. That's
So it's about the water resistance. It's not so much about the bracing strength, although it may. So I'd have to look at the product manufacturer literature and say what bracing strength does it have fixed in what scenario. But that's what you don't want to do is have that out to the weather. So that stuff takes in moisture fairly well and will swell up and everything. If that's all exposed to the the weather and moisture, it's not going to last. It's actually, I think it's H3. So it's designed, to be able to, be exposed to some moisture. But yeah, I wouldn't trust it as much as I trust the 5% sheet.
So OSB, that's basically just like wood chips that's been glued together.
Yeah. And you'll see that happening a lot with timber stuff now, is that a lot of it is about bits of stuff glued together. That hardboard right at the top here, that's lots of tiny little chips all glued together. So and everybody, there we go, there's some hardboard, and then you go right up the top. But you also would have seen MDF. Anybody seen MDF? So cupboards. MDF. That's medium density fiberboard. That's like lots of small fibres all together. So it's all processed, glued together. You've got the other stuff. I don't even know what it's called. That's used for the carcasses of your kitchens. There's like lots of larger wood chips all glued together. That gets moisture in there and it just swells up. So a lot of things that are made from wood that's processed. Just quickly, with your studs, they're going to be at 600 centimetres, typically. The reason for that is with a sheet roof, you have a rafter that lands on top of every second one. With a tile roof, you have a rafter that lands on every single one. If you don't have your rafter directly landing on top of your studs, that puts additional load on your top plate there. Your top plate needs to be thickened to achieve that. So you run two 90-45s around the top, so you can be dropping rafters anywhere rather than directly over the studs. But best design is always to have your rafters directly over studs, both for that transfer of load, because you want your loads transferred directly through a frame, but also for tie down. We don't have any pictures here showing tie down, but to ensure that our rafters aren't ripped off of our wall framing in the event of a really strong storm, we have galvanised iron strap that loops over those rafters and then ties it to the studs. That's the best way of doing it. So it goes over the rafter, around the top plate, and then tied to the stud directly. So any of that suction, that uplift force is transferred directly to the rafters. Directly to the studs. The studs are then tied down to our bottom plates by a strap that goes underneath our bottom plates and up to the studs. Those bottom plates are tied down to our slab with masonry fixings like Dynabolts or Chemset anchors or blue tips, which are these self-tapping masonry screws. So those bottom plates are tied down to our slab, and our slab can't be picked up off the ground. It's quite heavy, it's sort of on the ground. Or with our suspended timber floor, we have concrete, or we have some form of tile happening there. So studs at 600 centres, we'll fly through that. Sometimes we have studs supporting concentration of loads. We need to put extra studs in there to support those concentrations of loads. Noggins, covered that. Lintels, spoke about those, covered those. We covered those to a great extent in assessed in frame design. Top plate. This is how we go about calculating our bracing. So we have to look at the wind forces acting upon the building. The way the Timber Framing Code sets out our process for working out the way wind forces are acting on the building is to take in the whole vertical elevation area of our roof plus half of the vertical elevation area of our wall. So we take that in and go, that's how many square metres it is. For a hip end scenario, we look at one table and it says, can't even remember, but it's X number of kilonewtons per square metre. So we've multiplied the square meterage by the kilonewtons in that table for that particular wind speed. If it's a hip end roof, sorry, it's the gable end roof, then we look at a different table. It says this many kilonewtons per square metre for that area. So we calculate the square meterage that it's acting on, so this is square meterage, and multiply that by the figure in the table. It gives us our total number of kilonewtons of force that the wind is putting on the building. When we have that total number of kilonewtons of force, let's say we have 20 kilonewtons of force acting on a building. This one, if we get 3 kilonewtons of restraint per linear metre, we'll need about 7 linear metres of this bracing in any one direction to resist those kilonewtons of force. Another limitation of this bracing is, to be effective, those bracing straps have to be at a certain angle. If we do a really short section of that bracing, then that bracing ends up being on this angle like this, and it's ineffective. Or if we do a really long section of the bracing ends up being at that sort of angle and becomes ineffective. So there are limitations to the length our bracing can be. So it has to be, and this is working off the top of my head, so probably refer back to the Framing Code, but I think the minimum is 1800 millimetres, so you can't go short than 1800 millimetres, and the maximum is 27 or something like that. So you can't go more than 27. So it requires a certain size of wall, really, to get that bracing in there. If you've got a really short section of wall, you can't use this strap bracing. You can go to, there's a steel component manufacturer called Pryda, P-R-Y-D-A, that make lots of components. I definitely go to their website, get their product literature, keep all their stuff. That's something you just got to refer to again and again and again. Pryda, they have a strap bracing setup called short wall bracing. So if you use their products in a certain way, they've got their details there for using strap bracing in a short context where they've got X's stacked up on top of each other. So you can use it in a short wall section for certain engineered examples, and you can refer to that product literature for that engineering. But beyond that, typically when you've got short sections that need bracing, let's say we've got to provide bracing in the corners here like that, you're going to use sheet bracing. So that sheet bracing doesn't have those minimums of length because it's not on an angle, and that angle isn't affected by the length. But when we use very short sections of sheet bracing, we diminish the actual bracing capacity per metre of that sheet bracing. So once again, refer to the manufacturer product literature on how many kilonewtons of restraint you can get per size, but just be aware of that. When you go less than 900 millimetres, typically your bracing capacity is halved per linear metre for your sheet bracing. Also, just another quick note in regards to bracing, and this is bracing in a nutshell. This is not bracing that you would now go out and design with, by the way. Another important thing to think about with your bracing is start with your corners. That's where your bracing is going to be most effective. So when you do your bracing design, your bracing layout, think about the corners first, get your bracing in those corners, and then you work your way through the rest of the frame. Also, don't just have bracing on one end of the building, bracing on the other end of the building, and nothing in between. Your bracing should be spread out as well throughout your building, and timber framing code goes into the limitations around that. So it's like every 6 metres, so you have to have more bracing dispersed throughout the building. Permanent wall bracing and nominal structural bracing. So within your timber framing code, you've got your nominal fixings. You've got a table there that says nominal fixings are these, and then you look at your tables for uplift, for example, and it says for tile roof, you have to specify this fixing and then the rest is nominal. That's fine. Your nominal fixings, that's just your carpenters shooting nails in, pretty much. So as they're putting it together, they're bang, 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 shooting nails in. That's your nominal fixing. That holds the pieces of timber there. But your specified fixings are ones that you have to work through and say, we've got this much uplift, we've got these forces happening, we have to design that fixing to resist those particular forces. So that's the difference between your nominal and your structural.
Strap brace.
Strap brace?
Yes.
This one is a strap brace because you use galvanized iron strap for it. This one is your bracing board or sheet bracing. Okay. Also, so this strap bracing, that's what's called it's 30 by 0.8 galvanized iron strap. So 30 millimeters wide by 0.8 millimeters thick. Your 30 by 0.8 GI strap is going to be used in a lot of places in the building. So it's not just for bracing, you end up using it for tie downs as well. I don't know, there's a picture in here showing, oh there we go, that's a manufactured tie down, you're not going to get it that neat. So that's when you buy off the shelf. That's that company I mentioned before, Prida. That's probably one of their. Now I'm supplier agnostic, but just let you know that Prida is your main one for all these sort of products. But that's in absence of a better picture, you use your galvanized iron strap to loop over these elements to work as tie down as well. So, as I mentioned before, typically a lot of your wall frames are manufactured on site. So all put together on top of the concrete slab and then lifted up. Sometimes you get these things happening inside the factory, but for the mainstay, there's not a lot of efficiency in that. Well, the efficiencies in that aren't enough to account for why you do it in the factory. When you're working on a concrete slab or a platform floor, marking out is fairly simple. It's done by chalk lines or string lines with graphite powder in there that marks on the floor. Fairly simple. So you build everything down on the flat and then just tilt it up. When you're tilting it up, you have some temporary bracing in place. So that's the carpenter's job. And then, by and large, everything's done with machine-driven nails. Now, if you've got your nail guns, they just make everything really quick and really simple. I talked about stud clusters before, so you've got to think about what's happening in terms of fixing plasterboard. So this is for a brick veneer. We've got these two faces on the inside of the building for fixing plasterboard. On the outside, it doesn't matter, fixing nothing to it. But these pieces of timber here is what's called blocking. So that makes sure those two studs work in concert together. So they're essentially blocked at various sections to ensure they work together. So here's the various set of scenarios for your different stud clusters for different locations. If you get a chance to have a look at some wall frames on site, I suggest you do it. Of course, always get permission from the site supervisor and where your PPE is required at the site. But yeah, when you can get on sites, have a look at these details. That's the best way to see all of this stuff. But look for your things like your state clusters. Another thing about bracing is, particularly when you've got strap bracing, you've got loads transferred to bottom plates. Because as that strap bracing gets extended, it wants to make that bottom plate kick up. It's pulling on that bottom plate. So you need to have bottom plate fixings within 150 millimetres of where your bracing terminates to ensure that that piece of bottom plate there is held down. So that's either going to be a Dynavolt or a Chemset or a blue tip. Has everybody here seen a Dynavolt before? Everybody knows what a Dynavolt is? Some not. Yeah, most people. But for those that don't, it's a metal sleeve, and then there's a bolt inside of that with a bell end and the thread on the top. So you drill a hole, you can put it in there, it sits in there nicely, and then as soon as you start tightening up the nut, it expands the casing on the outside and grabs into that concrete underneath. Your blue tips are a really coarse threaded bolt. So you can drill a hole smaller than the shape of the blue tip and then just drive it in with a rotary hammer, or not rotary hammer drill, but a driver.
Impact drill.
What's that?
Impact drill.
Yeah, impact drill. Yeah. And that coarse thread will cut the thread into the concrete and lock itself in there. And that blue tip's got a little bit of glue or something like that on the end of it that as it gets hot, it helps that binding happen. And then Chemset anchors, they're anchors that you drill a hole out, you can clean that hole out well, you don't want any dust in there, then you put an epoxy resin stuff in there, and then you put the anchor in there and it binds to the concrete. Chemsets probably get the best binding out of any of these fixings, but it's far more labour intensive. Then got your frame in place, fix your windows. Those windows, the best way to install those is to use a little bit of packing there. Now, not everybody packs windows these days, but it's much better process. If I was checking someone's work on site, I'd like to see packing there. That helps transfer loads from windows into the frame. So if you've got kids slamming windows and whatever, that's directly transferred to the frame rather than the wall frame rather than the window frame taking all of that load. So that's your timber framing. Now your steel framing in the main doesn't deviate from all that. All the forces are the same. All the designs essentially the same. We've got studs, top plates, bottom plates. We've got bracing, and that bracing can be calculated as per AS 1684. The wind loads that are happening on the side of a steel frame are the same as what's happening on a timber frame. So your bracing can be designed the same, but what does end up being different with your manufactured steel frames is that quite often it's all designed by a computer with this design software and all cut by machine. It's very easy to do these things where you've got diagonal elements included within your frames. And then they can be steel to steel fixing is really easy with tech screws, so self-tapping metal screws that just fix everything really well. So you can have a little bit more complexity happening in your steel frames, and then a lot more accuracy in the manufacturing and the cutting of them as well. So that's going to make a bit of a difference. Beyond that, other differences between your steel and timber frames, the way that you run pipes in there. Your steel frames, if you look at them, a lot of them have got these holes in the centre of their studs. So when they manufacture that stud material in the factory, it's manufactured with holes in it. And those holes line up, so you can just run pipe work through the middle of those frames. Whereas when you've got a timber frame, your plumber has to come along with a drill and drill lots of holes. When it's a steel frame like that whole process is controlled. When it's a plumber coming in, cutting things, drilling things, that's not controlled. Hopefully they know what they're doing. They're drilling through the centre of everything, where the forces are closest to neutral as possible, but they may not be. One issue that happened with steel frames really early in their design and manufacture is that a lot of plumbers were just running pipe work, so you've got your steel frame stud at a C shape, and they'll just run their pipe work in that steel stud. And then the plasterboard fixers come along using screw fixings, they screw into the stud and straight into the pipe work. But because a lot of that pipe work is this PEX material, your screws will go into it and it won't leak. Because it's that malleable sort of plastic material, screws will go into it. And that'll be fine for 5-10 years until that screw ends up rusting out, and then there's water in your wall and nobody understands why until they pull it apart. So that was a problem with your steel frames. It started showing up sort of 5-10 years down the track from their early introduction. But those issues have been solved now by the manufacturers of those frames. That's pretty much, your differences. And of course on site, all the installation is going to be happening with self-tapping metal screws to lock everything in place. So we covered bracing. Yeah, so I just spoke just then about installation services. So yeah, your steel framing, it's got those holes in the middle. Still sometimes with your steel framing, you'll get taps being located and things like that. And so the framers or plumbers on site have to introduce little bits of timber in there. They'll just use a piece of timber for doing that because they can fix in through the sides. Also, we've only got 12 minutes left. What I will actually, in that 12 minutes, I will introduce steel frame floor systems as well. So this here is a steel frame floor system. So with our floor systems, we can use either a concrete, and in your project number 1, you're asked to compare a concrete raft slab on the ground, then your timber frame floor system, or your steel frame floor system. So I'll go into timber floors later, but in this short pocket of time, we can have a look at some steel frame flooring systems. So those steel frame flooring systems, that can provide a lovely flat floor manufactured in the factory, and then put together and then brought out as these separate elements, and then included on stumps. What I introduced to the Learn site while we're waiting this morning are I introduced 3 web links. One is to this page called Wood Solutions. Has everybody seen that page? Does everybody know that page? Cool. It's a massive resource. You could be up for, spend your nights for about a year reading all the stuff in there. Then I provided a link to this page, Spantec. They're not a South Australian company. They're based in New South Wales. They produce elevated steel frame floors. There are a lot of, so elevated steel frame floors, it's a relatively new thing on the market. Now, it's been done for a while, but in the last 2 years, there are a whole bunch of manufacturers jumping in on this. So probably in the next 6 months, we'll see other manufacturers in this space as well. We've got a lot of smaller scale manufacturers in South Australia, but we don't have any of the major market leaders here in South Australia. So we've got this company in New South Wales who produce a lot of steel frame floor systems, and I think they do. I think, once again, product agnostic, but I think they do a fairly good product. So that's quite, their systems are quite good, and their design and their information is really good, and they've got partnerships with people that produce the peering systems as well. So you can go, right, that's what I want, and they do the design, comes back to you. But they're in New South Wales. In South Australia, we've got, so this is a thing that's available through Bunnings. So you've got, Stramit are a manufacturer of a lot of your light gauge steel stuff. particularly roofing, so they do a lot of roofing, but they also produce this Steel Max modular floor frame system as well. And that's one that's more for the home DIY who's putting on a deck. So you go, okay, I want to build this deck, I want to do it myself, I'm a bit handy. Go to Bunnings, say, can you, this is the deck I want to do, can you do me a floor system for it? And they go, yeah, there you go. But you can also use these for your entire floor as well. So you probably can go to Bunnings to go, I want to do the entire floor for my house. You go straight to Strata and say, this is what we're doing. These are the set downs I want. This is the whole area we're doing. Can you design that for me? Through this link that I chucked on the Learn site, there's these two links there, which I encourage you to have a look at. One of them is download our Floor Frames product information guide. Otherwise, download our Floor Frames design guide. So I spoke, so earlier on in this subject, I get you to set up your OneNote and also your filing system for all this stuff. So just grab a lot of this stuff and organise it well so you can find it whenever you need it. But there's some good information in there. So looking at that product guide, tells you how it goes together. Keep flicking through. Gives you lots of information about the process of design or specification, but also about the limitations. So it says things like, you should not use this product within 300 metres of break and surf. So you go, all right, well I can't use that for my beach house. It says things like, well it's got its limitations for amount of roof load. So it says I can't find it in here. Quickly, I have to read through it, but it will say, roof loads not exceeding 6.9 metres or something at 2,700 high. So we go, okay, well we wanted to do 3 metre high ceilings and we wanted to have a large roof on it. Can't use it. So a lot of your limitations are set out in here. Well, and wind speeds of N3. So that maxes out. Now that's got to be most of the South Australia, but some pockets we've got N4 wind speeds. Can't use it there as well. And down the bottom here, it's just jumped up on the way. I'll just zoom in a bit and scroll down. Got this little thing, bearer span table. So and it tells you about the size of the panels. So when you're designing with a steel frame floor system, you think about designing it in terms of panels. So you look at, okay, what size panels are available? We've got panels up to 5 metres in width. And then further back here, it says you can do panels up to 12 metres in length. So the biggest panels you can do, 5 metres wide, 12 metres long. So that's actually a really big panel. And then it gives your bearer spans. The reason bearer spans is important to us as designers is because that tells us where we need to have our supports, our posts underneath. So if we're going to just use adjustable piers or something like that underneath, we look at this and we go, okay, for 5 metres wide, my posts have to be at 3 metres, 3 metre centres along my bearer, which is the outside member of those panels. Whereas if I shrink that down to 4.2 metre wide panels, well then I get away at 3.2. So it's about you doing those calculations, about working out what's our most efficient for our posts. Now, as you go along, as drafters and designers, you'll get a bit of a working knowledge of the cost of various different aspects. That's something that you really have to do yourself. There's programs like Cordell's and whatever that help you with that a lot. But eventually you'll come to a point where you go, okay, well a pier in this situation is going to cost me about $150 per pier. You go, all right, if I do this, well then sum them all up, that's what that one's going to cost. Or if I go this other solution where I'm spending a little bit more on the framing, but I'm saving on piers, it's going to save me this much money. So it's all going to be that sort of interaction. But you've got the bulk of your information you'd be needing to make those decisions within these various different design guides. So,
Why we can't just bring out a plane to that factory and say that it's their job to give us a quote, how much that is going to cost?
yeah, and you can do that, right?
That's easier.
Yes, that's easier. They'll charge you for it. That's so.
It's a quote,
Yeah,
they don't charge.
Yeah. Oh, okay. Then,
It's a
yeah.
quote.
Yeah.
No one
and-
charges.
Yeah. So yes, and definitely, and when it comes to steel frame, that's typically what you're going to do. But the reason it's important to understand these things is because if you bring a design, when you're designing, you're thinking about options, and you're thinking about, okay, we're doing this here, we're doing that there, well, what's going to cost us more money? You can make some of those decisions early in that design stage, whereas you're not going to take your things for quotes until you're relatively well through the design stage. So you design the whole thing and you go, all right, now it's ready for quoting. And you take it to them, you say, what's going to cost me for that floor frame? Whereas if you understand your panel sizes and things like that, you're making some of those decisions and thinking about those things at that early stage, you can go, well, do this, but if we do that, that's going to cost us more than we do this. You know, because this way we need to have more panel, more supports. You can have that insight from that information that's supplied. You make some of those decisions early on, and there might be a few $1,000s. So that's why. Well, it's one of the reasons why it's important. But also, you just basically have to know the most important thing is to know the limitations of these things. So you don't just take stuff for quotes and they go, oh, we can't even do that. You take other people's quotes, oh, we can't even do that. Whereas, it's going to waste
With
time.
experience, we will know if we are building a house, 200 square meter or 300 or 400, we will know, okay, 200 square meter usually cost, I don't know, 2,000 something that will cost. So, but this takes lots of experience.
Yeah, and that's it. You will get better at that. So I've got those two links there. By all means, check out a whole bunch of others, right? So you do a search for steel frame flooring systems, and not just on your first page that turns up on Google, but just pour through. You're going to find other small manufacturers. Actually, while I'm on that, so there was another company. I visited them over the break. It was in December. I headed out there. So there's a place out in Anato that build portable buildings. They were looking to go into supplying their steel floor. So they use these steel floor framing systems for themselves. So producing their own steel portable buildings. But they were looking to go out into the residential market as well, start supplying to builders and supplying to people. I was interested in this for a particular project, so I went out there and had a bit of a chat to them. Turns out they've decided, no, we're not going to open up and be supplying stuff to the public now. But they might do that in the future. So there's a place called Portable Camps. I think they would, if they start supplying stuff to the South Australian market, I think it'll be a decent, cheap alternative. But anyhow, but in the process of stopping out there, having a chat about stuff, I grabbed some of this. This is their engineering information for their limitations on panel sizes, etc. as well. So it's much like in your other design guides saying, these, we've got our various different panel sizes and panel widths and joist spacings and things like that. All that information you need for making decisions about flooring and post spacing and things like that. So there's that place, Portable Camps. But I'll just, there we go. They had a video in here somewhere, or here. This is in the Spantech. So they've got lots of information there about the design of their systems. Maybe I should have queued it up. They had a video that showed this stuff actually being made. I thought that'd be an interesting thing for you to see, but we're very much running out of time here now. So I won't show that video because I'm not sure exactly where it is in their website. But yeah, if you want to have a trawl around through there, a few different bits of videos and so on there showing how it's all made in the factory, the machines that are just rolling it, punching it, cutting it, etc., showing you that, and then also how it's all put in place on site. So how these things go up. So that's your steel frame floor systems. Now next week I'll have a bit of a discussion about suspended timber floors, and then we'll go on from that. And in that concert, in talking about suspended timber floors, we can talk about the pros and cons of steel and timber. Like, why would we choose one over the other in that instance? So during the week, have a look at all this stuff, get your research happening, get some work happening on your project one. So you should already understand enough about concrete slabs to be doing that whole section and that. You should now probably be armed with enough information to start thinking about your suspended steel floors, and also your timber trusses, your conventionally pitched timber roofs and things. So there's a few sections you can knock off over the week and check out these things. Quickly, I'll just stop the recording. Quickly beyond that, so I have